what I want to talk about. I first want to talk about gradient estimates for Ricci curvature. And then I want to talk about some closely related monotonicity for Ricci curvature. And after that, I'll get to gradient estimates for scalar curvature. Now, to put things in perspective, so there's a classical result of Cheng and Yau from the mid-70s that say that if you have a manifold with a non-negative Ricci curvature and you have a positive harmonic function on a ball, then in the center of that ball, you have a bound for the gradient of log of the function, and that is some dimensional constant divided by the radius of the ball. And so if you take the radius of this ball, if you let the radius of this ball go to infinity, then you recover Yau-Liouville theorem. So Yau-Liouville theorem was originally proven just on a complete manifold, but Yau-Liouville theorem can be deduced from this local gradient estimate. So this is a sort of fundamental tool on manifolds with non-negative Ricci curvature, generalizing the classical gradient estimates for harmonic function on Euclidean space. For the heat equation, there's also important gradient estimates, and so that's the gradient estimate of Li-Yau. And there again, you have a positive solution to so in this case, it's a positive solution to the heat equation on a manifold with non-negative Ricci curvature. And the gradient estimates in this case is that the gradient of log of the function, that squared minus the t derivative of log of the function, is less or equal to the dimension over 2t. T is the time that you have flown. And so this estimate of Li and Yau, this is sharp. And it's sharp actually on the fundamental solution to the heat equation. So the fundamental solution is this u of x of t equal to t to the minus n over 2 times x of minus the distance to the origin squared over 4t. Right, so we return to this in just a minute. So the Li-Yau gradient estimate, that actually is a sharp estimate, whereas the Cheng and Yau is not sharp. It's just say that there exists some constant, and it's not a sharp constant. Okay, now, so the three questions that I want to talk about is a sharp elliptic estimate, so a sharp estimate for harmonic function, positive harmonic function, just like the Li-Yau gradient estimate that is sharp on the heat kernel for the Mendel solution to the heat equation. Then I want to talk about integral analogs of this, like entropy for the heat equation. And then last, I want to talk about versions of this for scalar curvature. And so the result I want to talk about for Ricci curvature is in all dimensions, whereas for scalar curvature, it's only in dimension 3. And so this may be a good place to take a short break, like what Bernhard suggested.
Yeah, it's occasion for the audience to ask questions if anything is not so clear yet. But I think, I mean, this what you told us is very clear, I think. But anyway, we just want to make the audience participate so that we have some interaction.
Okay, so let me continue. Right, so this is sort of the setup. Again, these are the three things I want to talk about. And so let me start with some background and where some of these ideas and techniques come from. So the first thing I want to recall, so this is an old result of myself and Jeff Cheeger. And so this is about manifold with non-negative Ricci curvature. And it say that if you have something that behaves like a volume cone, almost like a volume cone, then it is almost a metric cone. So by this, I mean that if you take two radii, where the outer radii R2 is much larger than the inner radii, and you're looking at the annulus between this outer and the inner, and if the rescaled volume of the outer ball is almost the same as the rescaled of the inner ball, then the region in between is almost a metric cone. Okay, and for this talk, an important tool is on the annulus between the inner ball and the outer ball. It's a regularized distance function, and I'll come back to generalization of this in just a minute. A second tool that I will use is a weighted spherical average. And so this is going back to some work of myself and Bill from a long time ago. And so there we looked at if U is a positive green function with pole at P, we defined B to be U to the power 1/2 minus the dimension, n is the dimension. And then we define the spherical average, the weighted spherical average, to be where you're integrating over the level sets of this function B, and it's weighted by the gradient of B. And then there is the factor, which is, if it was on Euclidean space, it would be the scaling in the volume of the distance sphere that's in front. And so this gives you a family, because U is the green function. This gives a family of measures on different level sets of B. And the mass of these measures are the same. And so this again follows from Green's formula. And so we originally introduced these weighted spherical average to study growth of harmonic functions on manifolds. Okay. A third tool is that, so if you take any manifold and you take any positive harmonic function, then you can define a function B, where B is defined by that B to the power 2 minus the dimension of the manifold is equal to this positive harmonic function. And then you get this. So this is a paper of myself from 2012. Then you have the following key formula that will play an important role later on also, that if you take the norm of the gradient of B squared and you weight this with the positive harmonic function U, then it has this nice Laplacian of that, has this nice formula here. And you see, of course, that in the case where the Ricci curvature is non-negative, both of the terms on the right-hand sides are non-negative, right? And the first term is, of course, the norm of the trace-free part of the Hessian of B squared. Okay. So these are the three tools that I want to recall. And in particular, the third one will play, but in combination with the other, will play an important role. Another thing I want to recall is about when you have positive green functions. So a manifold is said to be non-parabolic if it emits a positive green function. And an old result from 81 of Veropoulos say that if you have a manifold with non-negative Ricci curvature, then it's non-parabolic if and only if you have this, that the integral of the volume of balls, so P is some fixed point, and you're looking at volumes of ball of radius r centered at this fixed point, and that goes in the denominator, and in the denominator you have r if this integral is finite. And so you see that this, to say that this integral is finite, is more or less saying that the volume of balls centered at some fixed point is growing faster than quadratic. So this, it's if you want to sort of formulate this in just a word, it's say that more or less that a manifold with non-negative Ricci curvature is non-parabolic, so admit a positive green function if the volume is growing faster than quadratic. And so using that and using this gradient estimates of Li and Yau I mentioned earlier, Li and Yau proved that if you take a manifold with non-negative Ricci curvature and it's non-parabolic, then for the minimal green function, you have that it's converged, it's positive, and it's converging to zero at infinity, and the gradient of it is also converging to zero at infinity. Okay, now let me talk a little bit more about regularized distance functions. So if I look on Euclidean space, and I take the Euclidean space, pointed Euclidean space, where I'm fixing the origin, and I'm looking at the function u of x, which is the norm of x to the power 2 minus n, then it's harmonic, it's obviously positive, and it goes to zero at infinity. And you have that if you integrate by Green's formula, if you integrate the gradient of u over a level set, then it's the volume of the sphere of radius of the unit sphere, so it's constant. It does not depend on the level set. And so if you, in general, right, for this talk, if you here satisfy A, B, and C, then we can define this regularized distance function B as u to the power 1 over 2 minus n. And so now coming back to the Cheng-Yau gradient estimates. So the Cheng-Yau, and this here again holds in all dimension. I will just state it because later on I will specialize anyway to dimension 3, but this here holds in all dimension. If you take a manifold with non-negative Ricci curvature, and I state it again in dimension 3 only, but it holds with obvious changes in all dimension. And we then define B as 1 over u, where u is this green function. Then the Laplace comparison theorem will tell you that B is less or equal to the distance to the pole. And so from the Cheng-Yau, so in this case of dimension 3, log of the gradient of B is up to a sign, the same as log of gradient of u. So if you apply the Cheng-Yau gradient estimates, then you have that the gradient of B is bounded by a constant. Right, the gradient of B is bounded by a constant using this with the Laplace comparison. And so, again, so this function B has a bound for the gradient. This bound here will be increasing in a dimension, and it's not sharp. So if you're looking at the function in the plane, which is x times y. This is in the quadrant, it's positive, And if you're looking at what Cheng-Yau gradient estimate gives you there, it will be, in this case, if you're looking at what the gradient of this function is in that quadrant where it's positive, you get square root of 2. And so again, unlike the Li-Yau gradient estimates for positive solution to the heat equation, this is not sharp. On Rn, if you use this, if you're looking at this function u here, that with these conditions here from this slide, where c is a way to normalize u, normalize the green function, then what you would get, on Euclidean space, you would have that the gradient of b would be equal to 1. Okay. And so this is the sharp gradient estimates of myself from 2012, that if you take any manifold with non-negative Ricci curvature, then the gradient of b, and again, b is defined from the green function, that you take the green function, you use the normalization in the usual, the normalization that gives you that this constant c here, the constant, so c give rise to, right, so this is the integral of the gradient, the norm of the gradient of u over level set, that is constant. And if you normalize the function, which we've done here, so that this integral is the volume of the sphere of dimension 1 less, then in that case, the sharp gradient estimate tells you that, so the sharp gradient estimate tells you that on any manifold with non-negative Ricci curvature, the gradient of b is less or equal to 1. And you have equality, if it's just at one point, the gradient of b is equal to 1, then the manifold is just flat Euclidean space. Okay, so this is a sharp gradient estimate for Ricci curvature. That is the parallel of the Li-Yau gradient estimate. Now, how do one prove this? And so the key inequality is this inequality that I talked about earlier, that where we're looking at this function b, we're looking at the norm of the gradient of b squared, we multiply it by u. And so this here is when the manifold has non-negative Ricci curvature, this is subharmonic. This function is subharmonic. And so what you then do is that you are looking at the function, this function, and you subtract 1 plus epsilon times u, where epsilon is some small positive number. And so u is harmonic. This other function, u times the norm of gradient of b, is subharmonic. So this difference here is subharmonic. And because of the way it's normalized, b is normalized as you, the asymptotics near the pole gives you that this function is negative very, very close to the pole. And it goes to 0 at infinity. And then the maximal principle tells you that this function is always non-negative, and this holds for each epsilon, and you let epsilon go to 0, and this gives you then the sharp gradient estimate. Okay. Now, this sharp gradient estimate is closely connected with some monotonicity formula. And so unlike the Cheng-Yau, that wasn't sharp, because it is a sharp gradient estimate, it's connected to monotonicity. And so the natural quantity is where you're looking at, where you integrate over the level sets of b, and you integrate the norm of the gradient of b to the power 3. And so the way to think about this is that you want to think about this as an average, a spherical average of the function that is the norm of the gradient of b squared. So you think about the weighted spherical average of that. And this is because the weighted spherical average is where the weight is the norm of gradient of b. So together with the weight, right? And since the function is the norm of gradient of b squared, then you get the norm of gradient of b to the power 3. Okay. And so this then connects to one of the results, one of the old results I talked about in the beginning, and that was sort of the motivation that was how I sort of found this monotonicity and the sharp gradient estimate, that to look for something so that the derivative, look for a quantity whose derivative is the distance to a cone. So if we just go back to the result, one of the results I mentioned in the beginning. So this is this old result of myself and Jeff Cheeger. That's where you proved that if something was almost a volume cone with the volume from inner radius to the outer radius, if the scale invariant volume hardly go down, then the region in between is a metric cone. Okay, and so the idea here is to find a quantity whose derivative tells you what the distance to the nearest cone is. And so this is sort of the idea. I won't get into how to actually prove that, but this is the idea of this quantity A and its derivative. Okay, now there are more, and it's one of the other more general monotonicity quantity that will play a role in this talk, later in this talk. And so again, these results hold. The one I will mention here next hold in all dimension, but I will just specialize it where n is equal to 3. So this is joint work with Bill from 2014, where we defined more general quantities. And so the one I looked at originally was where beta was equal to 2, but more generally, you can look at this quantity A beta, and the derivative of A beta is given like this. And again, if you specialize if you're looking at where beta is 0, then this is a constant by the divergence theorem. And so that constant is 4 pi, the way we normalized B. Okay. And so now we proved that for any beta bigger or equal to a half, this function A beta is convex. And so to see this, let me just talk about why it's convex when beta is equal to 2. So there you recognize on the right-hand side the key inequality, Laplacian of this function u times the norm of gradient of b squared. And so, but that's also equal to, you can easily see that that's the same as if you multiply that by u, it's the same as the divergence of b to the minus 2 times the norm times the gradient of the norm of b squared. Okay. And so now this implies if you're looking at an analysis between two radii, or two level sets of B, because the divergence is non-negative, and so you see that from the previous slide we have that the derivative of A2 is given by this formula where you're integrating over the level set of B of R. You can write this. So here I have, so we've taken out, you see the b to the -2, that was sometimes written as a weight out in front, but over a level set, that's of course constant. So you can just put it inside the integral. And because you can rewrite the derivative of a2 like this, what I've done at the bottom of this page, then using what the divergence of that thing is, that's non-negative, then you have in between two level sets of B, you have that you get that the derivative of A2 is non-decreasing. Okay? And so now convexity, so this is something about so this doesn't give you anything about the derivative here, but it gives you something about the second derivative. But the second derivative then implies monotonicity. And this is because so this is followed from that suppose that the derivative was actually at some point it was positive. Suppose it was positive, suppose it was bigger or equal to some delta. Well, then convexity would tell you that the derivative would be bigger or equal to delta later on. And so now if you integrate that, then you get that A here would be growing linearly as r go to infinity. But on the other hand, A here is bounded, and this is because you have a bound for the gradient of B, right? The gradient of B is bounded by 1. And you have that the average, that the mass of these weighted volumes is constant. So you have that for each beta, this A beta is always uniformly bounded by 4 pi. So it does not grow linearly. So you see that, in this case, convexity actually implies monotonicity, because if the derivative was anywhere positive, the original function would have to grow linearly, but the function is always bounded, so it cannot grow. So it cannot grow linearly. Okay. Now we use this quantity A2 and a related weighted version of the Einstein-Hilbert functional to study Einstein manifold or Ricci flat manifolds. So we used it to prove that if you take a Ricci flat manifold and where one tangent cone at infinity is regular, so smooth away from its vertex, then the tangent cone at this space is unique. Now, let me now get to some of the results about scalar curvature. So we have a manifold, three-dimensional manifold. So now, of course, from now on, it's important that we are in 3 dimension. So we have a 3-dimensional manifold with 0 first beta number. We assume that it has just one end, so that the level sets of this function function b is connected. And then we assume that the function, the green function that b comes from, goes to 0, and also the gradient goes to 0 and infinity. And so the result is that if you have such a tree manifold, then with non-negative scalar curvature, then the weighted average, so this is the weighted average of the norm of gradient of B, right? Remember that the weight is also have a norm of gradient of B in. So the results say that if you have a tree manifold with these properties, then A1 is always bounded by 4 pi, and you have equality for some R if and only if the whole manifold is flat Euclidean tree space. Right, so this is a kind of generalization of the sharp gradient estimates that I talked about earlier to scalar curvature. And but unlike the result I talked about earlier, it's not a pointwise result. It's say that the average is the weighted average of the norm of gradient of B is less or equal to 1. Right? And that's again because of that the A0 of R, this is always equal to 4 pi, right? And so this means that the integrand is less or equal to 1. Fine. And so if you also assume a lower bound for the Ricci curvature, then this was proven by Buchana Wang and Cheng, Chu, Li, and Zhang have a related result.
Toby, may I ask
Yeah.
you on the previous slide, under
Yeah.
which conditions do we have such function u?
Right.
So what are the conditions, or can one say something? So when are these?
That's right, and that's that's not. I don't have. I mean, it's a natural. It's it's a natural. I mean, so I don't think that any sort of general results that tells you that right. So the first are some assumption that right. So this was one end, and the first Betty number is some topological assumption, and
Mhm.
and they may be. It's possible that you can. You can. It's possible that you can weaken those. Uh, we assume that, of course, that you have a positive green function on the manifold, right? So
Mhm.
it's non-parabolic, right? And so they are natural assumptions, I think. You can, of course, the positive green function, again, at least the intuition for Ricci curvature is that the manifold should have faster than quadratic volume growth, right? But it's not like I can't tell you. I mean, they're pretty natural. I think I don't have general result that say that when you have it, right? But
Mhm.
again, you would expect. I mean, the most serious assumption is probably this with a positive green function. We certainly use that also the gradient goes to 0 at infinity, right? But of
Yeah.
course, yeah. But if you don't, and the reason why we want a positive green function that goes to 0 at infinity, and the reason for that is that we want the function b to be a proper function, right? So if u goes to 0 at infinity, since in this three-dimensional case b is 1 over u, this means that b goes to infinity at infinity, right? So this is for sure an assumption that is needed for these sort of results here.
May I ask him something? So
Yeah.
if you have some manifold and then you add connected some with bubbles, it doesn't change your conditions. So what happens with gradient on this bubble that goes to 0 very fast or what? The
So you
simple geometry. You start with
uh,
Euclidean space or almost Euclidean space.
and so the bubbles, I mean, you still have non-negative scalar curvature.
No, it still has positive scalar curvature. right?
Okay.
You can add bubble and you can take connected.
Yeah, that's right. No, that's a good point. And so that's right. And so that's right. And so right. So that's right. So the thing is that that's right. So the gradient, you expect the gradients to this is the same for Ricci curvature, that if you that if so for Ricci curvature, and you would have a similar phenomenon here. So for Ricci curvature, if you take a manifold with non-negative Ricci curvature and it say have less than Euclidean volume growth, then
but here it may have any growth, right? You can make
right. But you know what I mean? Like if you're changing it, you expect the gradient to go down, basically.
So on these bubbles, it goes to zero pretty fast, right? Because you may have exponential growth.
But it's like but typically what would happen is that the gradient is going down, but it's not just here; it's also further out. This is what happened.
Although the volume of manifold may grow super exponential fast, it doesn't vary. Right? It can make a huge mess. You can
I mean, in the case of Ricci curvature, for sure, that
no,
if
it's
it changes somewhere,
Ricci curvature, it can't happen.
It goes down. It affects
for
everything.
Ricci curvature, it cannot happen. Right? You cannot have
right. But you could still change the manifold, right? You could deform it somehow, right?
No, but very little.
I agree. You couldn't just insert a bubble. Yeah.
This is a fundamental difference. For Ricci curvature is basically rigid. You cannot change it too much. Given the volume, you can change it. And here, everything can be completely arbitrary volume-wise.
Right.
Volume-wise, distance-wise, well, not fully. But still, harmonic function, okay.
But you know, but again, I mean, we talk about these weighted volumes, right? And so the weighted with gradient.
Yeah. No, but that reminds of this estimate by Stern, right? For map to circles. When on the contrary, you do have non-trivial Betti number, you have harmonic forms, and then you have some inequalities, non-trivial inequalities for scalar curvature. Would what you say related to that?
I mean, I would expect, I don't know for sure, but I would expect that the gradient would go down, right? I mean, certainly go down in some weighted sense.
According to your theorem, it's supposed to go down.
Yeah, that's right. Okay, so right, so let me right, so okay, so now let me talk about how right, so how do we prove this? So we prove the following key results, that if you take if you take a manifold, so this does not actually use that the gradient also of U goes to zero. That if you take a manifold with a non-negative scalar curvature, if you looking at if A1 for some radius gets strictly bigger than 4 pi, then we prove that A1 would actually have to grow quadratically. But since the gradient of U is equal to b to the -2 times the norm of gradient of b, then and so then this would give you a lower bound for the gradient of U for the average of so it would give you an average lower bound for the gradient of U, and that's impossible if you have that the gradient of U goes to zero in infinity. Right? Okay, so this here again. So this is like this more general result that gives you that if the A1 is strictly bigger than 4 pi, then A1 would have to grow at least quadratically. Right? And so that's impossible if you also have that the gradient of U is going to zero at infinity. Muciano Wang, what they proved is they prove that A1 is growing linearly if A1 get above 4 pi. Right, so I'll just very briefly mention have been quite a lot of other terrific results using our functional A1 very recently. These are just a list of some of these results. Now let me talk a little bit about the proof. So if we're looking at the level set of B, then the unit normal to the level set is the gradient of B divided by its norm. The Laplacian of B squared and the trace-free part of the Hessian of B squared, those are, so the Laplacian of B squared is equal to 6 times the norm of the gradient of B squared, and a capital of boldface B is the trace-free part then of the Hessian of B squared. And so on R3, where B squared is with this normalization, where B squared is the norm of x squared, then the trace-free part is 0, and the gradient of B squared is 2 times the position vector. So those are the dilations. And so we have this formula that the derivative of A1 times the radius on the level sets is equal to 1/2 times r to the power minus 2 times the integral, and then that's of this trace-free part of the Hessian of B squared evaluated in the unit normal direction. And so you see that A is constant if B here is if this trace-free part of B is 0, and but it's only 0 on flat Euclidean space. Okay. And so you have again this, so this is written in a different way. You have this crucial Bruckner formula for the Laplacian of U times the norm of gradient of B squared. And you see that only the Ricci curvature in the normal direction comes in. And so we're using a trick of Cheng and Yau to rewrite this Ricci curvature in the double normal direction in terms of the scalar curvature, the intrinsic sectional curvature, and the second fundamental form. And in 3 dimension, we let S1 be the integral over the level set of the scalar curvature. B2 is this integral of the norm of B squared over the gradient of B squared squared. And then you get this formula here that's assuming that the level sets of B are connected, you get this inequality for the derivative of A1. And so, of course, you see that so B2, right, is non-negative. S1 is also non-negative because it has non-negative scalar curvature. So if you throw away S1 and B2, then you have this differential inequality. And so once you have this differential inequality, this will tell you that if A1 here gets above, if A1 get above 4 pi, then A1 will grow, and it will grow linearly, okay? Now, in general, if you take a function that is like a polynomial to the power p, and you're looking at r times log of the derivative of log of this function, then this will give you the degree. So in general, this quantity here, r times f prime over f, is like the polynomial growth rate of the function f. And so if to say that a1 is, that we want to prove that a1 grows quadratically, this just means that this quantity alpha of r, which is r times a1 prime over a1, that is roughly 2. And so maybe I'll just skip this one here. This is just a little bit about some earlier, the linear growth. Yeah, maybe the Muchano-Wang that I mentioned, that's the linear growth. That can be in this way, can be rephrased as that alpha is bigger or equal to 1 minus this 4 pi over a1. And then this other earlier results that gives a green function proof of the positive mass theorem can be rephrased in this way. And so the one that we have, which is stronger than both of the previous ones, is this inequality for alpha prime. And so just to say a few words about that, to say just a few words about this inequality for alpha prime. If we take a trace-free part, so a trace-free 3x3 matrix, and we evaluate at some unit vector, then you have this inequality here. And so this is using that. So the first inequality is like the trivial inequality, where instead of restricting in both slots to this unit normal, then the second slot you take over all vectors, right? And in the second inequality is using that this matrix is trace-free to get this constant 2 over 3. And so using this, you can prove this inequality for a1 prime. So you get that that a1 prime, the square here is bounded in this way in terms of a1 and b2. And so if you divide by a1, then you get a1 squared, then you get this inequality. Remember what b2 was. B2 was this quantity here. Again, the ball face b is the trace-free part of the Hessian of b squared. Okay, and so now putting this all together, it gives you this differential inequality for alpha prime. And so to understand this quantity here, like the last term here is the last term in this inequality, the 4 pi over a1. That's of lower order, and this is because a1 is growing at least linearly, so this is of lower order. So you get heuristically that if alpha here was strictly less than 2, then the inequality above will tell you that alpha prime would be growing. So this means that alpha would be, alpha prime, would be positive, right? So this means that alpha would be growing, right, at a rate. And so this could not really happen for very long, right? And so integrating this, you get a lower bound for alpha, which is this lower bound. And that actually is good enough to give you quadratic growth of A1, right? So that A1 is growing quadratically. In the last few minutes, let me just talk a little bit about what we earlier used. So I mentioned this briefly, but what we earlier used, the quantity in this case. So this stuff here is about a quantity A1. Again, and so these results here was about this quantity A1. And again, A1 was where you take the norm of the gradient of B and you take the weighted average of that, and that weighted average have another norm of gradient of B in it. So, but let me just talk about how we used one of these other monotone quantities. So we used this earlier. That's suppose you take a manifold, or open manifold, which is Ricci flat, and has Euclidean volume growth. So in this case, the volume of balls grow like some constant times r to the n. And so if you take a sequence here of ri's and letting ri go to infinity, and if you scale the metrics, then of course those are also Ricci flat. And so by Gromov compactness theorem, if you take such a sequence going to infinity, you can rescale the manifold by this sequence and extract a convergent extract a convergent subsequence that converts to a metric space. And any such metric space is a tangent cone at infinity. And so the results I mentioned earlier show that any tangent cone at infinity is actually a metric cone. And so what we proved using the monotone quantity A2 was that if one metric cone is regular, so smooth away from its vertex, then it's unique. And to prove this, we used a weighted Einstein-Hilbert functional that looks like this R here, which is minus this quantity A2, and then the weighted total scalar curvature. So this is the intrinsic scalar curvature of the level sets. Okay. And so again, for this, you want to think about this functional as a functional on pairs of metrics and weights. And we prove Weiershevitz inequality for this functional. And using that, we proved that this quantity A2 converge to a limit, and you get a rate that is converging to. And then you used that, again, as I talked about, the derivative of these functionals, of the functional A2, the derivative of the functional A2 gives you a distance to a cone. So once you have a rate that A2 converts to a limit, then you get some weak information about that the derivative to some extent is also converging, and that gives you then that it's converging to a cone of a certain rate, and that gives you then uniqueness. So that was just a quick overview of some of the things we used these functional to. Okay, so I will stop here.